Okay, here we go. Once again, look at the particular problem, try to work the problem out, then watch the video and let's compare answers, right? You can always stop the video. So, the question is, a sociologist found that in a random sample of 40 retired men, the average number of jobs they held during their lifetime was 7.2, and the population standard deviation is 2. So we are told that we have a sample n which is equal to 40. We have from that sample x bar turned out to be 7.2, and we're given the population standard deviation is 2. That's the information given. The best point estimate for the population mean is the sample mean. So the best point estimate is 7.2. Question B. We want a 95% confidence interval for the mean number of jobs. So we're looking for a confidence interval. Our confidence interval, look it up, is going to be x bar plus or minus z. Why are we using z? Because we know the population standard deviation times sigma divided by the square root of n. In other words, 7.2 plus or minus. If you look up z for a 95% confidence interval, go to the table, and you're going to find out that there's 1.96 times the standard deviation, 2, divided by the square root of n, which is 40, and the interval turns out to be 6.58, comma, 7.82. You should be in a reasonable neighborhood about those two numbers. Alright, C, we want a 99% confidence interval for the mean. Again, confidence interval. We know the population standard deviation. So again, the same formula. And therefore, here it's going to be 7.2 plus or minus. The z-score for a 95% confidence interval is 2.576. Multiply that to the standard deviation divided by the square root of 40. You do the math, and you're going to come out with the interval 6.39, comma, 8.01. Okay? So let's move on to number 2. Move on to number 2. We have a sample of 15 randomly selected commuters in Chicago, and it shows the average commuting time was 33.2 minutes. Standard deviation was 10. We want a 90% confidence interval for the true mean. So we have a sample that consists of 15. We have that from that sample, the average commuting time was 33.2, and the standard deviation was 10. The standard deviation is from the sample, not the population. We want a 90% confidence interval. So in this case, we are going to be working with the t-distribution, okay? Since we have S, we're working with the t-distribution. So there's really no difference in the formula itself, other than we're going to have to look at the t-value. And for the t-value, we need to know the degrees of freedom. And those degrees of freedom is 15 minus 1, 14. 1 less than the sample size, right? So you look up the t-value, you can do that. And t turns out to be 1.761. So, again, key word here, confidence interval. Key point, sample standard deviation, t-table. But again, the formula looks very similar. It's going to be the mean plus or minus the t-value times the standard deviation divided by the square root of n. When you do your math, you should have the interval 28.65 to 37.7. Okay? Moving on to number 3. The mean salary of a federal government employee is $59,500 with a population standard deviation of 1,500. The average salary of 20 randomly selected state employees do similar work is $58,800. We want to test the claim that state employees' true average salary is less than that of federal employees. And we want to use a test of a 10% level of significance. That is, alpha is equal to 0.10. So what's your hypothesis? The hypothesis is the status quo. That is, it's no different. The claim is that it's going to be less than. So here's really what the claim is. That mu for the state employees is going to be less than what the population is getting in general, which is the 59,000. Remember, 58 is associated with the sample. It's going to be used in the test. But we always work with the null hypothesis is that there is no difference. The status quo remains. So there's the null hypothesis. Mu is 59,500. The claim is it's actually less. To calculate our test value really is, quote, a z-score. Okay? Now it looks a little bit different, but the test value is based upon this formula. X bar minus the mean associated with the null hypothesis divided by the standard deviation divided by the square root of n. And in this case, n is equal to 20. What I like to normally do is collect my data, so let me do that. Mu is taken to be 59,500, right? Sigma is equal to 1,500. Alpha, 0.10, right? And n is equal to 20. But there you go. I always like to collect my data, really. But let's just plug everything in. So if you plug it into the formula, x bar, okay, well, I didn't write x bar down. X bar is equal to 58,800, right? So get your information, plug it in, and you're going to come out with a test value of minus 2.088, somewhere around that, all right? Now, the critical region is dependent upon the alternative hypothesis. We're going to reject if our sample is such that it posed that test value significantly lower than 59,500, meaning that here's the 59,500. If we are significantly lower, meaning if we're over here somewhere, that would suggest that yes, there is a significant difference. What is this point here? Well, we know the population standard deviation. So we're going to be working with a z-score. Since the level alpha is 0.10 and it's a one-tailed test, if you go to the table, I have the table somewhere here. You move it over. I'll show it this one time. But it's a one-tailed test. Alpha is 0.10. I think I forgot. Look, 0.10. Yeah, 0.10. So it's going to be the second column here. So it's going to be the second column here. It's a one-tailed test. So we go down. The degrees of freedom is equal to 19 because the sample size was 20. So we go down to 19, and here's our value. Hold on one second, make sure. Alright, mess up. We're doing the z-table thing, so it's at the very bottom. Okay, I had to go back and look at the problem again. But we know the population standard deviation. Okay? Since we know the population standard deviation, the bottom of the table is our z-score. So it's 1.282. So going back to our problem here. Okay, going back over to our problem. We know this here then is negative 1.282 because we're on the left side of the mean. So we're below it, so the z-score is going to be negative. So there's our critical region. If you look at your test value, it falls in the critical region. So the conclusion is we will reject the null hypothesis with a 10% chance of committing a type 1 error. Okay? Meaning that we rejected when we should not have. Alright? Now the second one is no different other than we're changing the level of significance. So again, since we are working with a z-score and it is a one-sided test, we're going to be rejecting if we're below it. But we're working with a z-score, so now let's go back to our table. That's up here. But we're working with a 0.01. It's still a one-tailed test, so we go to the very bottom here, and it's 2.326. So that's going to be our endpoint of the region of rejection. So moving down here, we know this point here is negative 2.326. That test value no longer falls in the rejection region, meaning the test value is over here. And since it's in the region of non-rejection, we do not reject, okay? All right, let's move on. Get this thing going here. Number 4, again, key thing here is a hypothesis test. The null hypothesis, if you read the problem, I'll let you read the problem here. The null hypothesis is nothing different. And the null hypothesis is that on average, it costs $5,400 for braces. Okay? The claim here is that the cost is different from the average. That is, mu for the particular franchise is not going to be $5,400. Your test value, again, is going to be x bar minus the mean of the null hypothesis divided by sigma. But in this problem, excuse me, we don't have the standard deviation for the population. We have x bar is equal to 52,500. We have S, the standard population of the sample, is 629. So the only difference here is this is S over the square root of n. When you calculate this, you're going to come up with a test value of minus 1.261, or 2, I think it's 2. Okay, 262. Okay, after you plug your numbers in from the particular problem, and that's just calculations. The important thing here is knowing the critical region. Here you don't care if you're below or if you're higher. If you're far enough away from that mean, 5,400, then you're going to reject. So this is a two-tailed test. Not equal is a two-tailed test. So what is the test value? Well, once again, if you go look up in the t-table this time, because again, we do not know the population standard deviation, we need to work with the t-score, and so therefore the degrees of freedom in this particular problem is 27, because n is equal to 28. Look up the degrees of freedom. You're going to be looking under a two-tailed test with a alpha value of 0.1, and if you look that up, you're going to come out with 1.703. So over here, it's negative 1.703. The test value here is not in the region of rejection, so we do not reject. Okay? The last problem, which I treated as extra credit, is associated with proportions. Now, in this particular problem, we have a random sample of n equal to 205. 65 students believed that places could be haunted. That is, the proportion of students, which is denoted by p hat in the sample, is 65 over 205. This is approximately equal to 0.3171. So Q hat is 1 minus that, which is 0.6829. Once again, we're trying to find a confidence interval, a 99% confidence interval. The formula for the confidence interval associated with a proportion is p hat plus or minus the square root of p hat q hat divided by n. That's the formula. We know what p hat is. We know what q hat is. N is 205. Plug your numbers in. Do the math. And you're going to come out with an interval that is 0.233, comma 0.400. Or somewhere very close to that, depending on how much you've rounded, okay? But it shouldn't be off by 1.01 at the most, okay? Otherwise, you probably rounded by far too much. But anyway, that is the confidence interval. The key here is to identify the type of problem. You want a confidence interval? Okay, if it's a proportion, there's only one formula here. Okay, and I think I might have left off my z value. Sorry, there's a z value here, right? The z score. I kind of left that off my notes, so I do have the z. Look up the formula. This is unedited. Again, I'm basically saying I don't have time to edit this, especially right now, but I left off the z here, and that's part of the formula.